Hello friends, welcome to this fifth video on complex integration where we are going to see about application of Cauchy residue theorem to evaluate real integrals. We have an intro of the evaluation to real integrals already in our part 4 video. We will try to solve one more problem using a different function of cos and sine in this video. We will take the prerequisites as the Cauchy residue theorem. It says integral over the curve C, closed curve C, f of z dz is 2 pi I times addition of the residues of the function f of z at its poles. Now the residue can be evaluated as limit z tending to a z minus a into f of z for a simple pole, and limit z tending to a 1 by n minus 1 factorial d power n minus 1 dz power n minus 1, that is the n minus 1th derivative into z minus a whole power n into f of z for a multiple pole of order n. Next, moving on, the basic requirement for the type 1 conversions are cos theta to be replaced by z square plus 1 by 2z, sin theta to be replaced by z square minus 1 divided by 2iz, and d theta to be replaced by dz by iz. So having these yellow portions to be memorized and the prior quantities of the formulas to be in memory, we move on to evaluate the next problem, which is given as evaluate integral from 0 to 2 pi d theta divided by 13 plus 5 sin theta. Now this is going to be representing a type 1 problem of real integral where I have integral from 0 to 2 pi. You have a function of a cos theta, a sin theta with respect to d theta. So I have my conversions which are available for cos, sine and d theta already ready in my previous slide. So I'll have to substitute them, and in which case I will be converting everything as a function of z. So I will be evaluating over the closed curve C, where C is going to be the closed circle mod z is equal to 1, the unit circle. What do we mean by unit circle? A circle with radius to be equal to 1 unit. So this is going to be my converted boundary after the substitution. So now let us get started with the substitution. So the integral from 0 to 2 pi will be converted along the closed curve C along the boundary mod z is equal to 1. D theta will be replaced by dz divided by iz. We have 13 plus 5 times of sin theta to be replaced by z square minus 1 divided by 2iz. So this is going to be the conversion. Let me make the simplification. So I have dz divided by iz. 13 2s are 26 iz plus 5 into z square minus 5 divided by 2iz. Iz over here can be cancelled off with the iz in the denominator, pushing this 2 to the numerator. So I have 2 dz divided by, let me take the common term 5 outside, hence we will be left out with z square plus 26 by 5 times of z minus 1. So now my problem has been entirely converted into a function of z. So for this function of z, I can apply the Cauchy residue theorem and then evaluate what is going to be the value of the integral. So we will quickly recollect the steps involved in the Cauchy residue theorem. Step 1, find the pole. Step 2, identify what is going to be the boundary. Step 3, find whether the poles lie inside the boundary or outside the boundary. Step 4, estimate the residue of the function at the poles. And step 5, apply it to 2 pi I times summation of the residue. So that completes the process for us now. So we will now move on to our step 1. What is our step 1? Identifying what are going to be the poles. We have the function to be equal to z square plus 26 iz by 5 minus 1. So z square plus 26 by 5 iz minus 1. This is my function. We will equate it to 0 to get our poles. So this is going to be my first step. So z is given by minus b plus or minus b square minus 4ac, the whole root divided by 2 times of a. So this gives me minus 26 by 5 times of I, that is going to be my coefficient over here of z, plus or minus plus 26I by 5 the whole square minus 4 into, this is going to be my A, so let me mark this as A, this is going to be my B, this is going to be my C. So what will happen to my C? C is going to be equal to minus 1, the whole square root divided by 2 times of 1. So I have minus 26I divided by 5 plus or minus 26 square is going to be 676. I square makes it as minus 1. So minus 676 divided by 5 square makes it as 25. Minus of minus makes it as plus 4, the whole square root divided by 2. Let me take the LCM, in which case this is going to be minus 26I by 5 plus or minus 676 plus 5 into 25 makes it as 100, the whole square root divided by, when this 25 comes outside the square root it becomes as 5, the whole thing divided by 2. Let me simplify this furthermore. So this becomes minus 26I plus or minus 676 plus 100, the whole square root divided by 5 comes to the denominator from over here, and already there is a 2, so that gets to be equal to 20. So minus 26I plus or minus, this makes it as minus 576, the whole square root divided by 10. What do we know about square root of 576? This is going to be equal to 24, and with a minus sign inside the square root, this turns out as I divided by 10. So the poles are minus 26I minus 24I divided by 10, or minus 26I plus 24I divided by 10. So now this makes it as minus 50I by 10, or this makes it as minus 2I by 10. Hence the poles are finally obtained as, this goes over here 5 times minus 5I, or you can have this to cancel off 5 times to have minus I by 5. So my poles have been obtained as minus 5I and minus I by 5. Now how I can rewrite my denominator as, the denominator can be written as z plus 5I, z plus I by 5. So this is how my function will be now replaced. So this can be replaced as z plus 5I and z plus I by 5 after finding my poles. Along with it, what do I have? I have a 2 by 5. So now this function becomes, so I have to plot my step 2, identifying the boundary mod z is equal to 1. So this is going to be a circle with center 0, 0 and radius to be equal to 1 unit. What are going to be my poles? My poles are going to be z is equal to 5I minus 5I and z is equal to minus I by 5. In the coordinates, this turns out as, the real part is 0 because minus 5I can be written as 0 minus 5I, in which case I can write as 0 comma minus 5 as the x comma y coordinate. Minus I by 5 can be rewritten as 0 minus I divided by 5, real part being unavailable, so 0 comma minus 1 by 5. So the second step, we have identified the boundary. The third step is to find the position of the poles in the boundary. What is going to be my first pole? 0 comma minus 5. 0 minus 5 in y-axis. Where is going to be minus 5? It's over here. Do you think that lies inside the boundary? No, it lies outside the boundary. So this pole which is going to be 0 comma minus 5 or z is equal to minus 5i lies outside the boundary. Now considering the second part, which is the second point, 0 comma minus 1 by 5, which is less than 1. So where will this lie? This will lie over here. So this pole which is going to be z equal to minus I by 5 lies inside our unit circle. So when it lies inside the unit circle, we say that the residue is, for the lying outside, the residue will be equal to 0. I'll have to just find the residue for the pole that 5 which is going to lie inside. So what is going to be my step 4? Step 4 is going to be finding the residue of the function f of z at the pole z is equal to, what was the pole that lie inside? Minus I by 5. And what type of pole is it? It is going to be a simple pole. So we will try to recollect the formula for the residue as z is equal to limit z tending to a, z minus a into f of z. So when I am going to apply this for my function, I'll have to first retrace my function f of z. What is my function f of z? You can move over here to find it. Integral over the circle 2 by 5 dz, integral over the circle C, 2 by 5 times of dz. The denominator over here was replaced by the quantity z plus 5i, z plus I by 5. So we will replace this as z plus 5i and z plus I by 5. So my function f of z, when I write the function, there will be no integral for it. So I will be having just this to be my function f of z. So this is my function f of z. So now let me estimate the residue at limit z is equal to minus I by 5, which is given by limit z tending to minus I by 5, because this is the only pole that lies inside. So you will have z minus of minus becomes plus I by 5 into your function of z. So limit z tending to minus I by 5 z plus I by 5. The function f of z, you can just paste it from over here. 2 by 5 z plus 5i z plus I by 5. Now we notice that the pole cancel off each other, and so we just have limit z tending to minus I by 5. The leftover quantity is 2 divided by 5 into 2 plus 5i. So in the next stage, we will apply the limit to the value of z tending to minus I by 5. 2 by 5 z plus 5i z plus 5i. So now when I apply the limit to my z, this gets replaced as minus I by 5 plus 5i. So let me take the LCM. So the LCM will be, this is going to be 1, 5 5s are 25 times of I. This 5 goes to the numerator, which can be cancelled off. So I have 2 divided by 25i minus I makes it as 24 times of I. So this can be cancelled off over here to give you 12i. So this becomes my residue at the point z is equal to minus I by 5. And what do we know about the residue at z is equal to 5i? Since this lies outside, it becomes the value to be equal to 0. Now my step 5, the value of the function f of z dz by my Cauchy residue theorem is nothing but 2 pi I times summation of the residues of f of z. So it is 2 pi I times your residue 1 plus residue 2 So it is 2 pi I times 1 divided by 12i, and the second residue was 0. So this I can be cancelled off, 2 can be cancelled off 6 times, leaving you with pi divided by 6. Hence integral over c d theta divided by 0 to 2 pi d theta divided by 13 plus phi sine theta evaluates to 5 by 6, pi by 6. So this is how we have used our Cauchy residue theorem to evaluate real integrals which are going to be bounded by a unit circle and containing functions of cos and sine. Thank you.